We live on the cutting edge of physics, material science, engineering, and nanotechnology. Because at Lockheed Martin, we're engineering a better tomorrow.
Okay, so when I was your age, and I mean the kids in here, I did not even know quantum physics existed. So you're super nerds. Kudos to you. I will give you, I guess, some background on myself. And to start with, we should start with the most important slide of today, the one thing I want all of you to take away, which is how to pronounce my name. It's Spiro, like Spiro, not Spyro. This is Spyro. Very friendly dragon. How many of you have actually played the game? Wow, that's awesome. So, unlike Spyro, I grew up in Greece. Greece is a beautiful place, especially during the summer. And growing up there with my older and younger brother, we would go every summer to where my mom is from, the island of Mytilene, the second largest island of the Greek islands. And we would play beach volleyball until we dropped. We were like so tired, we'd just go back into our rooms, and they would start playing video games, and I would start doing math. I know, right? It makes sense. I love doing puzzles. It was just so much fun to have a bunch of math puzzles that even adults could not solve, right? It was not about the knowledge that you had. You know, it wasn't about learning calculus and trying to solve these. These were the kind of things that, using elementary mathematics, just like basic arithmetic and geometry, you were supposed to find a way to solve them, right? But they were usually impossible to solve. So that passion turned to an addiction for me. And at some point, I remember even in junior high, I would stay up until 3 or 4 in the morning doing these puzzles, right? Working on these math problems. And of course, my parents thought I was watching TV. So they were very upset that for like many years, I could not wake up on time for school. They thought I was just up watching TV. They did not know, right, that I was doing all this math. So my dad would just drive us like a madman every morning just to make it on time. But this led, I guess, to the place where I went for my undergraduate degree. So I grew up in Greece, and then I left right after high school to go to this place, right? We've seen maybe other speakers here that have been to that place before. So they say when you go to MIT, it's like drinking from a fire hose, right? There's so much information, there's so much awesomeness coming at you so fast, and there is nothing you can do. You cannot escape it, right? There's no way. You're just like taking it all head in. And I started with computer science because my older brother was already there. He was also a nerd like myself. And he was studying computer science, so I thought, what do you do when you're at MIT? You should do computer science. But I remember taking a class on algorithms, and it didn't have enough math. And I love math. So I went to my advisor and said, I need to change my major. I don't want it to be computer science anymore. Right? I like computer science. I like programming. How many of you know how to program in here? This is great. I did not know how to program when I went to MIT. It was a very painful experience. Okay? That's not the reason, though, why I wanted to change my major. So he suggested that I take a different major. It's called mathematics with computer science. So I stuck with it, but there was a lot more math. And it was really exciting, right? I learned a lot of stuff, or so I thought, until I graduated. Okay, so I never actually took a notebook to class. I don't even know why. This is crazy, right? I didn't even have a backpack. I still don't have a backpack, right? I forgot what it meant to have a backpack and a notebook and taking notes and highlighting stuff. I just did not do any of that. So when I graduated, I actually looked back and I was like, what did I learn? I remember there were books and stuff, but I would even just borrow them from friends. I wouldn't even buy them. I ended up doing well, but the funny thing is that what it ended up doing for me is it gave me a very strong foundation in problem solving. And this is probably the most important thing, right? At least for me. You can learn a lot of stuff, right? A lot of trivia. You can become the master of Jeopardy or something, right? But if you're given a new problem, how do you even go about solving it, right? It's step 0 that is the most difficult step. What do you even do if you don't recognize the words of the problem? You don't even know what that means, right? And you have nobody to go. You cannot just go to your mom or your dad and say, hey, can you just help me solve this? It's just too hard for anybody. And the kind of research that we do, and that we'll talk about, it's so hard, we don't even know if any human will ever be able to figure it out, right? But at the same time, so much fun, we're not going to stop. We just keep going. So I applied to graduate school because I didn't know what else to do, to be honest, after I graduated. And it was painful. I got rejected from every single one of them, but 2. One of them was NYU, and it was actually, ironically, the top place in the country for applied math, which is what I was applying for. But they didn't accept me as a PhD student. They accepted me as a master's student. And then conditionally on that, if I did well, they would allow me to continue on to a PhD. But that meant that I had to pay for out-of-pocket for my master's degree, and that was very expensive, right? So there was another school that didn't even reject me. They didn't even send me a letter back saying, we don't even like you, right? Like the other ones. That was UC Davis, okay? Which is where I went to graduate school. So here's what happened. I called them. You should always call people when they don't respond, okay? Don't text them or email them, just call them. Face-to-face kind of thing over the phone. And I asked, okay, so was there a problem with my application? I never received anything from you. It was already too late. And they said, you're not serious, right? I mean, you're not going to come here if we were to accept you. I was like, why would I apply if I didn't want to go there, right? They had a great program in bioinformatics and evolutionary biology, which is a lot of the research that I did as an undergraduate at MIT, right? But they said, okay, no, I mean, if you're serious, just check your email in an hour. I'm like, okay. They had sent me over email an amazing offer, right? So I was going to be a PhD student at UC Davis. And it's a really beautiful place. If you like biking or if you like sushi, that's the place to be, okay? So I did a PhD in applied mathematics. But when I was there, I had an issue with my advisor. He was not there, right? The one that they had actually assigned to me was so famous in evolutionary biology, he was always somewhere, but not on campus. So I couldn't have him sign my coursework, right? And you need to have somebody to say, yeah, this is good, this looks good, you're going to be doing well, you need to advance to candidacy at some point so you can start writing your thesis and doing research. I couldn't find the guy. So I went to the head of the mathematics department at UC Davis, and I said, I need some help here, right? Can you sign it? He's like, yes, I can sign it. In fact, I'm responsible for this. Like, what do you mean? He's like, I made sure that you would become my student and not his student, right? So would you like to work with me on quantum teleportation? On quantum teleportation, right? Yes. Yes, I would. I will do it for free. I don't care, I don't even know what that means, but yes. So I spent some time, right, to see what that even meant. I hadn't taken any physics. Remember, I was in mathematics and computer science with biology even, right, undergraduate at MIT. I knew about these things, but beyond AP physics, I hadn't taken any physics whatsoever. And here I was asked to do quantum physics in graduate school, okay? So I went to Wikipedia, and I asked, hey, how hard is quantum physics, right? And this is what I got back from one of the founders of quantum physics, Niels Bohr, right? If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Well, I was not shocked, okay? So I needed somebody, that was like about 100 years ago, come on. Since then, maybe Richard Feynman, right? How many of you know about Richard Feynman? Yes, a good number. Well, maybe this dude would actually have something better to say, right? It's more recent. Nope. Nope. It's not going to help, right? Should I still do it? I mean, it's teleportation, it's Star Trek, right? So then, of course, what do, right? When you're not sure what to do with your life, you ask your mom. And your mom, of course, is going to say, now, here's how the intelligence that you're given comes into play. As you saw, before my name, I have a doctor, right? Dr. Spiros Michalakis. So she was happy about that. It's just I never told her, if she has a heart attack, I am useless, right? But a Ph.D. means a Doctor of Philosophy. Good enough for my mind. OK, so if we're going to talk about quantum physics, I guess, first of all, beyond just do you do it or not, right? How many of you would actually go into quantum physics? Let's see some hands here. Yeah, I thought so. You're just hiding. I know you want to. But what is quantum? Right? What is actually quantum? Okay, it comes from the Latin quantus, which means how much, right? And I bet that when you think of quantum, you're thinking of something microscopic, something subatomic, right? Something like that. You're trying to measure something, and it's in discrete quantities, right? OK, so here's how I view quantum. These are my top 10 favorite quantum facts, right? Number 10, quantum is big. Unlike what you thought, right? Quantum is not just at the atomic scale or the subatomic scale, quarks and so on and so forth. You can see quantum effects up to this level. This is 5 micrometers. And you may say, like, all right, well, this is about the width of a human hair. It's not that big, right? OK, but until now, we thought that quantum was only at the realm of atoms, right? So let's see, to get this into perspective, what this would look like. That bridge that you saw before, right, is to an atom, like this bridge here is to you, OK? So imagine that you want to go across that bridge. And you're just walking along, you're taking your time, but at some point, the bridge just splits into 2 bridges, like at the same time, right? Not like, oh, they built another one. It's like you're going through both at the same time, OK? This is what they actually did in this experiment over here. This was at Caltech by a couple of colleagues of mine. They took this small bridge, and they put it they cooled it down to its quantum ground state, so it was actually vibrating. It was in 2 places at the same time. And they could actually see that by sending light, and the light was going through both bridges at the same time and coming back interfering with itself. Right? When it wasn't cooled, the light was just going down one path as expected. Right? So it's as if we could put this bridge into this quantum superposition, which brings me to number 9. Quantum is in superposition. Right? And superposition is what I described before, where you can be in 2 states that you thought are like very distinct, right? You can only be in one or the other at any one time, okay? But quantum tells you that you can be in both, and in fact, most often, you are in both of these states at the same time. So how does that work, right? And why is it that we never get to see this stuff ourselves? Wouldn't it be really cool, right, if half of you were not here right now, so I would feel less stressed, but the other half were here, but at the same time, the other way around? I mean, that'd be amazing, but you're too large. We're too big. We're not quantum, it seems. But I just said quantum can be big. Okay, so what's happening? You don't get to see quantum effects like this superposition because we interact. All these quantum objects that have this intrinsic richness to them, right? Can be in many places or many states at the same time, they interact with everything else around them. So when I said before they cooled down this little microresonator to almost absolute 0, what they end up doing, what that means is you block it out from the rest of the universe. You're like, no one is going to disturb you. No light is going to hit you, no other radiation, no vibration or heat. You just like shield it from everything else, and then it becomes, again, quantum. It always was. It's just that you wash away this quantumness, these amazing properties of that object, when everybody is asking questions like, what's happening? Where are you? Right? And the answers are like yes or no. They're not maybe. And that's why things are the way they are. Right? The universe, everything, the lights, me right now, is interacting with each and every one of you. So you're here, not in the other room, kind of thankfully. Right? OK, so the third one is that quantum is actually really, really random. Right? That's an interesting one because how many of you know Albert Einstein? Right? Do you think he would ever be wrong about anything? Yes, right? Like his hairdo was not as cool as he thought, for example. He was a ladies' man when he was younger, believe it or not, right? Weird. OK, so what did he say? He said quantum mechanics cannot be a complete theory of nature. We're missing something because there is this inherent like randomness, it seems, right? God does not play dice. You cannot, I mean, he thought that everything already exists and it has a particular like state, right? It's here. It's not here and there until you like look at it, right? It's just always there. We just haven't seen it yet. We haven't asked the question to get the answer. So it's not as crazy as like when we're not looking, that other sign is in Spanish. It is in English no matter what, right? That's what he thought. It kind of makes sense, right? But then again, Niels Bohr is like, just lay off, OK? Don't tell God what to do with his dice. Sage advice, right? Because it turns out that quantum physics is really intrinsically random. It's not that we don't have a good enough machine or understanding of it, right, to be able to get the answer we want. At that level, at the level when things are really quantum, you just don't know. There is just a probability of thing being here or there and so on and so forth. But what happens is these probabilities can be higher for certain states or positions, I guess, in space, and much lower for other ones. So when you think of me, right, my probability distribution is picked right around here. Okay? Exponentially decaying, really, really small, that I'm actually there right now, or just disappear, right? If you close your eyes, we can try this, but anyways. Okay, so number 7 is one of my favorites. Quantum is entangled, right? How many of you actually have heard of quantum entanglement? Wow, that's really cool. Nice. So entanglement. Here is something that is a very recent experiment by the Austrian experimental quantum physicist, Anton Zeilinger. What does he say? He says, normally, you need to collect light bouncing off of an object to see it, right? Now, for the first time, you don't have to do that. That's insane, okay? It's like we turn off all lights here, and somehow you can still see me. Somebody asked at some point, oh, can cats see in absolute darkness, right? And you're like, of course not. I mean, it doesn't matter how good their eyesight is. If there is no light coming in, whatever the wavelength of the light is, right, it doesn't matter. There is no light. So this is what we're seeing here. The cat, it is a cat. It's supposed to be Schrödinger's cat, right? The cat on the right was illuminated, I guess. This is an image that the camera received from light that was never close to the actual cat, right? The cat on the left. So it never even went close to that cat. But what happened? The experimentalists, being crazy as they are, they split that original beam of light into 2 parts. One of them on the left went and interacted with a cat, right? The one on the right is what you're seeing there on the right, never even knew there was a cat, but then somehow created the picture of the cat. Why? Because they actually had entangled, later on, the 2 beams of light, right? So the one on the left that actually saw the cat passed the information immediately to the other beam of light and created that image, which is ridiculous, right? Forget about just seeing around corners. This is seeing ghosts, okay? So that's entanglement. It's like this strength of correlation between these quantum objects that it doesn't even matter how far apart these objects are in space. They're just connected, right? Whatever happens to one, the other one just knows. Quantum is powerful. So let's see how powerful it is, right? All right, take out your paper and pen. I'll give you a few minutes. So if I'm not mistaken, the NSA has a bounty for $100,000 for anyone who can factor not exactly this number, but a number like this, about 304 or 9-digit long, right, number. All I will tell you is that this is the product of two prime numbers. Prime numbers are those that are divisible only by themselves and the number 1. Okay, that's what it is. The building blocks of all other numbers. So you're not going to figure this out. Even with your best supercomputer right now, it would take you like 500 to 1,000 years, okay? And you don't have that much time because you have better things to do, that's all. But here are the two numbers, right? Because once you have a quantum computer, this should take you about a second, right? You can check later, that if you multiply these two, you'll get the previous one. Now, how did I do it, right? Obviously, I have a quantum computer. No, that's not true. I actually just multiplied these two numbers I found on the internet, and then But the point is this. The point is this, that this is actually how cryptography works. Right now, if you send a message over the internet, or if you want to buy something without everybody knowing what your credit card number is, or what you have in your email, or Skyping with your friends, or Snapchat, obviously, right? They would be able to see all that information if they could do just this, right? If they could figure out these two numbers from the previous number that I sent you. Because that's what is done right now, right? The trusted parties, what they have is the original big number and just one of these two numbers. Okay, and they could just do division, figure out the other one. That becomes the key, the cryptographic key that they use to unlock the safe, right, and get the information. But it's very easy to do it one way. You could just multiply these numbers in a second. Like probably you would do it like, yourself, in an hour. Or you could do it faster than that. But not in a millennium, right? The other way around, to figure out what these two numbers are, will take a lot longer. So quantum computer would allow you to do something like this. And this was one of the original algorithms we figured out that made us really excited to build one. And we're working on one right now, right? And we're not the only ones. Like at Caltech and other universities, we are at the place for the first time ever in human history that industry has become excited about building one of these machines. So we have Google right now, the Google Artificial Intelligence Lab, right? Microsoft, they have like a huge global effort behind this. They're doing some amazing work. You have IBM, right? Some of the biggest companies, tech companies, are trying to build one of these really hard, okay? Because it will allow us to do not just this, but also quantum chemistry, which allows us then to build better drugs much faster. And so on and so forth, like, searching for extraterrestrial intelligence, all the stuff you've heard about. This little machine is going to allow us to do. And this is just because it's based on the previous principles I talked about, superposition and entanglement, right? All right, so quantum is playful. Why am I saying that? I'm playful, right? Well, I helped build like a mod for Minecraft to introduce quantum physics, right, within the game. And I did that in collaboration with Google. They actually came to me and said, Spiros, they actually said Spiros, but it's okay. Spiros, can you help us promote quantum physics to the public? It was just when they were starting their efforts on quantum computing. And I said, sure. It's like, well, can you help us make a video? I'm like, that's boring. Let's make a game, Of course, what game would you want to do? Zelda. You would want to do Zelda. But, Zelda is kind of older, I guess. So they suggested Minecraft, and I thought they meant Minesweeper, which was embarrassing. By the way, quantum Minesweeper is a thing. It's out there. I did not build it, but it's very frustrating. Can you imagine, like, you're trying to figure out where the bomb is, and it's there or it's not there? It explodes anyways. It did not take off for some reason. So anyways, QCraft, right, we thought, like, how can we put some of these elements, right, superposition, entanglement, some of this randomness into the game? And, well, here's a little video, I guess, to show you how. So we demoed that at Minecon. Anyone here has ever been to the convention? Yes? Nice. It's insane. You have 10,000 of you in there, and pretty much everybody wanted to play this game, right? So we were there for 3 days straight with like 30 laptops going around the clock. But my favorite student was this one, okay? She came to me and said, I'm here with my granddaughter, and she seems to be really good at this game. Can you help me? So, we worked on this for 10 minutes, and then she was asking for the plasma gun at the end of this. I'm like, that's it, not the kind of game you thought it was. It's a different kind of game. But she became really good at it. It was heartwarming, right? Now we're getting into some crazy stuff. So quantum is spaceless. And this is something that most physicists don't even realize. Right? I read just yesterday an article in the Boston Review, an amazing article actually explaining quantum field theory without using any math. I was like, wow, this is incredible. But the author kept saying, well, quantum fields, which are these like electromagnetic field, for example, you're probably familiar with that. There is something permeating all of space and time, and at its place in space-time, there is a value to this field, right? And he said there's nothing more fundamental, as far as we know, than quantum fields. Particles come out of this one as excitations of quantum fields and so on and so forth. And I'm thinking, nah, quantum mechanics doesn't actually have any space embedded in it. What does that even mean, right? There's no, what is more fundamental than space? Where do you put stuff if not in space, okay? That's where math comes in. That's where my background in mathematics helps, right? Because we know that there exist mathematical spaces where there is no such thing as geometry or distance between the mathematical objects in there, right? Kind of like thinking that somebody gives you a basket of fruits and says, okay, just tell me which banana is closest to which orange. And you're like, I don't even know what that means. You mean like here next to it? It's like, no, maybe with respect to color or size or something else. It changes what we call the metric, right? The way we measure the distance between these objects. So in mathematical spaces underlying quantum physics at the most fundamental level, there is no such thing. There's just blobs. Quantum blobs we would like to call qubits, quantum bits, right? And all they do is change from one state to another one. Plus, they have the ability to be in two states at the same time, superposition, right? And they could be entangled, right? How? Well, let's just take this one blob right there in the middle, right? And you would think, okay, what happens if I hit that blob and it changes to a different state? Which ones around it are going to feel that change, right? And your intuition probably would tell you, well, okay, what if like one of you here wants to punch the person next to you? Don't do it, okay? You have a chance of accomplishing your goal and then running away, right? But if it is the person like 3 rows behind you, that's not going to work. They're too far away, right? But what if it is backwards, okay? What if it is that this distance, this illusion of distance, comes from the strength of correlations between the two objects? The stronger the correlations are, the closer we think of them as being, right? So for example, here, I hit 1. It's not the closer ones that are actually responding, right? The ones that change color in lockstep with this middle one are like the ones that you see out there, right? So what do we do as humans? We're like, all right, wait a minute. I don't want to have to keep track of all this stuff every time. Like, let me bring them closer. I want them to be closer so I could keep track of them more easily. What about this other one, this one in the corner there, number 2? What if I like hit that with a hammer and it changes, goes boom? These other ones, well, let's bring this closer too. And you're doing the same thing with every single one of them, and all of a sudden, you have reinterpreted your space from what you started with, which was all over, right? But in a way now that they're close to each other, but we interpreted them as being close simply because whenever one did something, the other ones also responded. The other ones outside of different color didn't even care. Right? So you would like to think of this as being something that is close enough so you can have an effect on it. Okay. So quantum is also in the movies, and as you heard, I was the science consultant for Ant-Man, and I saw a bunch of you actually watch that. It was kind of a fun movie, I thought, right? The physics was insane because I was the science consultant, right? But the thing that I found exciting about this is that we introduced the quantum realm, a place where the laws of physics, space and time themselves, the arrow of time, right? They don't have any meaning. They haven't emerged yet. They haven't appeared, right? What I showed you before hasn't happened. So you can be in all places at the same time, going back and forth in time, and so on and so forth, right? So we will see more of that in upcoming Marvel movies and other movies that I have something to say on. Number 2, almost there, quantum is part of life. There's amazing research in quantum biology, and it's something very recent. So for those of you interested in biology, I will touch upon, it has to do with bird navigation, how birds know, where to fly, using magnetism and the way actually that light penetrates and changes proteins in their eyes. There's also part of photosynthesis, how electrons know where to go and how to go there really fast, so you can create energy. Our own smell is quantum. That's crazy. Then you have enzymatic reactions that happen really fast because they use quantum effects. And then finally, we're just starting to really consider the idea that our own consciousness has quantum effects in it, right? Not just like things that just disappear because it's too hot in there, but things that are actually important for us to be thinking and the way we're thinking. And number 1 is this. Quantum is just the beginning. If I'm right, quantum physics is not the end of the story. There is another theory, deeper even on quantum mechanics. And it will be all of you, right, that will have to actually figure out what that is. I will give you a hint. You will need to learn some math, right? That's about it. So in closing, I just want to say, this is for all of you, right? And you should take advantage of this because this is an amazing revolution in physics happening right now, where we're considering for real that space and time are not even real, right? So you will be the ones to figure out what that even means. Thank you.